Hello and welcome back to Complex Analysis. And as you might know, first I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Now in today's part 12, we look at more examples for holomorphic functions. In particular, we look at examples that are given by a power series. Because we have already learned, a power series is a holomorphic function on its open disk of convergence. Also, you know, in the best case, this disk is the whole complex plane. Now, please remind yourself, holomorphic just means that the complex derivative f prime exists everywhere. Moreover, we also have shown that f prime is then also a power series with the same disk of convergence. In conclusion, this means that f prime is also holomorphic. Hence, the second derivative, f prime prime, does also exist. And by the same reasoning, it's also a power series with the same disk of convergence. So you see where this goes, all derivatives of f exist and are holomorphic functions. Okay, this is something you really should remember. It's a strong result that holds for holomorphic functions that are given by a power series. Indeed, later we will see that for all holomorphic functions the higher derivatives exist. But first, let's discuss some important examples. The first one, again, should be the exponential function. Here you already know, x of z is given by a power series from k is equal to 0 to infinity. And then we have z to the power k divided by k factorial. Now I know the radius of convergence you have already calculated and we get r is infinity. This means that the exponential function is an entire function. So we know that the derivative of the exponential function exists everywhere and we can calculate it. We simply can do this in the series term by term. Hence here k comes in front and we reduce the power by 1. So you see, this is not complicated at all. However, here please don't forget, k is equal to 0 corresponds to the constant term which always vanishes for the derivative. In other words, the new series now should start with 1. Okay, now the nice thing we should see here is that we can cancel this k with k factorial. Therefore, in the denominator, only k minus 1 factorial remains. So now this is a very nice expression, and you see we can do an index shift to simplify it even more. So instead of starting with 1, we start with m is equal to 0 again. And here please note, the new index m should represent k minus 1. Hence we have z to the power m divided by m factorial. And with this result, you see we get the original exponential function back. So taking the derivative does not change the function. In fact, this means that all the derivatives of the exponential function are the same. And this is an important property you should remember. Okay, then let's go to the next example, which is the cosine of z. And of course, we also define this function via a power series. However, this one is a little bit special because only even powers of z occur here. For this reason, we have to use the number 2 times k here and here. Otherwise, you should recognize it's very similar to the exponential function. However, there's also another difference because there is a sign involved. So you see, some powers in the series get a minus sign. For example, z to the power 2 gets a minus sign. Then z to the power 4 is plus again, and z to the power 6 gets a minus sign again. Okay, there we have it. This is the definition of the complex cosine function. And then I think you don't have any problems calculating the derivative similarly to before. Therefore, I would suggest that we do something else here and look which connection we find between the exponential function and the cosine function. Indeed, we find something with the help of complex numbers because I squared is minus 1. For this reason, one idea would be to put I times z into the exponential function. This is not so complicated because we have the whole power series here. Then what we should see is, here in the numerator, we have essentially 4 different cases. We get this because the powers of I have a periodic structure. So maybe let's start with the simplest case when k is equal to 1. Then we simply have I times z to the power k. Of course, this is not so surprising, but the same thing happens when k is equal to 5. We simply have this because I to the power 5 is I again. And of course, this also holds when we increase k by 4. Okay, there you see, we have one case where the factor in front of z to the power k is simply I. Now, in our next case, this factor is minus 1. Of course, this happens when we square our imaginary unit I. So it holds for k is equal to 2, k is equal to 6, k is equal to 10, and so on. Okay, by having this, you already see the next case should be k is equal to 3. Hence, we need to know what I cubed is. You can say it's I squared times I, therefore simply minus I. Now, with this, only the last case is missing, where we have k is equal to 0, 4, and so on. So let's put this case at the top, and then you should know I to the power 4 is simply 1. Therefore, in this case, the factor in front of z to the power k is just 1. Okay, so you see, this is very nice, but please keep our goal in mind. In order to get from the exponential function to the cosine, there shouldn't be any I involved. And also, only the even case should matter here. Therefore, we have to get rid of these two cases here. And the idea is to do this with another exponential function. It turns out putting minus I times z into the exponential function helps a lot. Of course, the power series here looks very similarly to before, and we also can consider 4 different cases. So maybe we can discuss them very quickly, because we only have to multiply with the factor minus 1 to the power k in these cases. Hence, for the even numbers we don't change anything, and for the odd numbers a minus 1 is included. So let's copy the cases there and there, and add a minus sign for the odd cases. Hence minus here and plus there. Okay, so you see here, our idea is now that we look at the sum exponential iz plus exponential minus iz. Then you see, the terms where I is involved will simply cancel out. And only the terms with an even k remain. Then you see, this is almost what we want for the cosine. Okay, maybe to make the whole thing here clearer, let's use the index m again. Now, please recall, only the even powers are involved, so our exponent is 2 times m, and in the denominator we have 2m factorial. However, please be careful, we also have a sign involved depending in which case we are. Hence, we have to add the factor minus 1 to the power m. Moreover, also please don't forget, we have the addition here, so we add the 2 cases. Or to put it in other words, we also get a factor 2. Okay, now we are finished, and you see, with the exception of this factor, this is exactly our cosine of z. Of course, that was our goal. Now we have the relation between cosine and the exponential function. This is very nice, because we can also use this relation to calculate the derivative. So first, let's state the formula again. Cosine can be written as 1/2 times exponential iz plus exponential minus iz. Then of course, we can simply use the chain rule to calculate the derivative of cosine of z. Now, the inner derivative gives us the factor I in front. This happens for the first and the second exponential, but the second also gets a minus sign. And otherwise, we can simply use the fact that the derivative of the exponential is the exponential again. There we have it. This is the derivative of the cosine. And you might already know, this should be minus sine of z. Hence, also for the sine, we now have a representation with exponential functions. And now these two representations can be very helpful when you do calculations with cosine and sine involved. Simply because powers of exponential functions are easier to deal with than powers of cosine or sine. However, in our course here, it's very important to know that exponential function, cosine and sine are all holomorphic functions. Okay, I think that's good enough for today, and I really hope that I see you in the next video. Have a nice day and bye!